As I mentioned, we're going to consider overall 3 failure criteria, 1 for brittle, 2 for ductile materials, and let us start with the first one, which is for brittle materials. Now, in all cases, the name of the criterion will suggest not only the type of material you can apply the criterion to, but also how exactly you should formulate the function that delivers the effective normal stress. So the name of the first criterion is maximum normal stress fracture criterion. Now the keywords here are 1, fracture. So it's not yield, it's fracture, and therefore I immediately understand that this must be for a brittle material, which means that when I formulate my criterion, I will ultimately calculate a effective normal stress and compare it against the ultimate strength of the material, because it is a brittle material. So the critical stress is the ultimate stress. 2, the criterion says that I should be monitoring the maximum normal stress at a point within a structure. Okay, so therefore, the way the effective normal stress is going to be calculated is through a function which tells me or delivers me the maximum normal stress among all stresses. Which stresses? Remember, we're assuming isotropy throughout the whole discussion of failure presently, and therefore I'm just going to take the principal stresses because their orientations don't matter, and I will look at the maximum value among 1, 2, and 3, okay, in absolute value. So this, therefore, is my function that delivers the effective normal stress. So that is now a failure criterion for a brittle material, which is typically sensitive to the maximum normal stress. So if you remember or see the name of the criterion, you should be able to formulate the failure criteria in the form of the stencil. The stencil is F delivers sigma bar should be less than or equal to the critical value. We've chosen the critical value to be the ultimate strength, and the function is suggested by the name of the failure criterion, right? That's where it comes from. Okay, so notice that it's in the form of the stencil always, and this is a very special function, the function that delivers the maximum among all principal normal stresses, and therefore I'm just going to put here a index and subscript that identifies this or gives this function a special symbol, and likewise the effective normal stress here is calculated according to this criterion, and that's what N indicates, just to distinguish it from some other effective normal stress that possibly comes from some other criteria. So that is the stress that that is the criterion we're going to apply to a brittle material. Now, subsequently, I can of course calculate the safety factor for this criterion. Again, N indicates that we have a normal stress criterion, and the safety factor is sigma u over sigma bar N. Now, having said that, now I will do something that will always remind us how to eventually determine what the critical limit to this structure, to this material behavior is. So what I will do is, I will replace for a second this sigma u with a critical value. That is, if you like, as yet unknown, because that is the form of our stencil. The stencil says, you give me a function that takes sigma 1, 2, 3, spits out a equivalent value, and I compare it against a critical value. Now, the name of the function suggests what I should be monitoring. I should be monitoring the maximum principal stresses among the three, and I'm looking at the absolute value. We'll make a comment on that absolute value shortly. So the max among sigma, the principal stresses, is the equivalent normal stress, and I should be comparing that against a critical value. The critical value certainly has to do with the ultimate strength, but if you're not sure whether it should be exactly equal to the ultimate strength, and in some cases you will see with the case of yield, the critical value will be a function of the yield strength, but not exactly equal to the yield strength sometimes. And therefore, what I will do now is I will try to deduce what that critical value is. And the way I will deduce it is always fall back to the idea is that critical value comes from a uniaxial tension test. And in a uniaxial tension test, if I pull, the material is ultimately going to fail at a point which is equal to sigma u, the ultimate strength of the material. And in this case, there is only one stress. Let's call that sigma 1 if you like. And therefore, the corresponding strain is a principal strain, which is epsilon 1. Then I plug in that test into this criterion. This criterion works for, according to our proposal, any possible state of loading, including combined loading. However, if it cannot predict correct failure limit for this very simple state of stress, which is uniaxial state of stress, then it's good for nothing. If it doesn't work for the simplest possible scenario, it possibly cannot work for a more complicated scenario where there are multiple stresses present. So I take the scenario, put it in there, and in that scenario, therefore, sigma 2 is 0, sigma 3 is 0, there is only sigma 1, and therefore its absolute maximum value cannot exceed the ultimate strength, and that's how I know that critical value is equal to the ultimate strength of the material. And that's why I've written it directly. Now, this nice argument we're going to fall back to again in the future when we talk about the ductile failure criteria. Okay, but presently that's our criterion for a brittle material, and that's our corresponding safety factor. So now one relevant issue that is associated with failure criteria, or one relevant concept, is the concept of a failure surface. Remember, conceptually I've talked about the limit to the extent of the elastic domain. So what is an elastic domain? So we can sort of visualize that picture with the concept of a failure surface. So what I will do now is I will take a very specific case, and let me highlight that it's going to be a state of plane stress. So I'm going to assume that sigma 3 is equal to 0. So plane stress with respect to the principal loading directions. So therefore, there's only going to be sigma 1 and 2 that could possibly cause failure. Okay? And what I would like to do is, I would like to have, or I would like to plot in the 1-2 plane in the sigma 1, sigma 2 plane, the combinations of all possible sigma 1 and 2 that eventually cause the material to break. Okay? And the locus of all points eventually will constitute what we will refer to as the failure surface. So let me explain you what I'm trying to say here. So first, for instance, I start from a state of 0 stress, and I keep increasing this stress only along the one direction without ever loading in the second direction. So I move in that direction slowly. Remember, sigma 3 is equal to 0. And at some point, the material will break apart because it is a brittle material. Okay, so that's the point where it fails. What's that value equal to? It's equal to sigma u. Okay, then I do the same thing by taking the material and loading it in the other direction, in the 2 direction. And I keep loading only in the 2 direction until failure occurs. What is the failure value? Well, this is also uniaxial loading, not in the 1 but in the 2 direction. So the failure strength is again equal to sigma u. Then what I do is I start loading the material in a direction that is skewed to either direction, let's say along that direction, and I proportionally load sigma 1 and sigma 2. So in other words, I move along a line in the 1, 2 plane. I increase sigma 1 by a certain factor, I increase sigma 2 by the same factor. So I'm moving along a line, and I keep moving until the specimen fails. Every time, of course, in this test, I'm using a new specimen. So as a consequence of sigma 3 being 0, I see that sigma bar n is equal to simply max sigma bar 1, sigma 2, because the other one is 0. So that's the criterion I'm using, right? So eventually, therefore, I'm interested in when failure might happen. So to see that, what I can do is I can draw a line that has a slope of 1. In fact, let's do that in both directions. And I see that here, because I'm below the line, the value of sigma 1 at any point is always larger than the value of sigma 2 at that point as I increase proportionally both of them. So this criterion for this loading line will spit out max of the two being equal to the value of sigma 1 because it's positive. And therefore, the value of sigma 1 cannot exceed the ultimate strength, and therefore failure will happen again at the ultimate strength. And for that matter, any value that is lying, any line, loading line that lies below the green line will give a failure value for sigma 1 being equal to sigma u. And by the same argument, if I'm above the green line, then failure, if I load along such a line, failure will occur when I hit sigma 2 equals sigma u for any loading line that lies above the green line. And therefore, this is the limit to which I can do a combined loading of sigma 1 and sigma 2. And again, by the same argument, the sign of 1 and 2 really doesn't matter, and therefore I can carry out the same or copy the same picture into the other planes as well. And this now is what we refer to as the failure surface. The failure surface, remember, it is special to, in this case, I'm drawing the failure surface for sigma 3 equals 0. And the failure surface gives me the locus of all points that eventually lead to failure. And this surface has been drawn according to my mathematical criterion. Now, there are several questions to ask here. Is this a good failure surface? Well, always my answer is it's a good model. In other words, it's a good surface to the extent that it can predict reality. Now, what you can do is you can actually take specimens and not do this conceptual experiment with that criterion, but actually do the experiment with actual materials. And suppose you load along certain lines and you find combined stress values that lie, let's say, in the first quadrant in such a manner. There will always be experimental scatter, but what we are saying here is that when I load along the line, failure happens there, failure happens there, failure happens there. And we see that the red line, our theoretical prediction, is a good approximation of what happens in reality. So the failure surface, the theoretical failure surface, is of course accompanied by an experimental failure surface that gives us the data. So that's our model. So the data gives a failure surface. We're just trying to approximate that with the smooth failure surface, smooth in the sense that it's a line, piecewise line that comes from our model. And the quality of that prediction depends on how well you fit the data. Now, do we fit the data in general well? Well, for brittle materials, we're saying that materials fail due to the ultimate normal strength of the material. So that's the prediction of that model. So which means that when I do a uniaxial loading test with a specimen, this is a rubber specimen, but nevertheless, let me take it. I pull on it and the specimen will break when I reach the ultimate strength of the material. Well, the plane that is associated with the ultimate strength is essentially the plane that is normal. This is the plane. The normal stress is in the normal direction to this plane. and therefore that stress is exceeded. When that stress is exceeded, the material fails in a brittle fashion, which means it will fail along the plane on which you have maximum normal stress. So I expect fracture surface to look like this if this is a good criterion. So now here is a simple experimental result with a tensile test specimen that is actually a brittle polymeric specimen. We pulled on it and it broke with little or in fact no plasticity. And what you see is that it broke on the plane with maximum normal stress, which happens to be along the direction of our loading. So this criterion apparently is a good criterion for brittle materials. All of them, I don't know, but at least for many of them. Now, one final remark. We've drawn a failure criterion into which goes the absolute value of the principal stresses. So the way the failure surface looks is the same in all quadrants. In reality, materials tend to have a higher strength under compression than in tension. In other words, if I were loading along that direction, I would hit a failure value that is further into the compressive zone. So in other words, the picture when the stresses are compressive are a little bit misleading. So nevertheless, what we're saying is I go along that direction and I fail at minus sigma u. Well, in reality, what you observe, in particular for brittle materials like concrete, that's a typical example, it doesn't fail at minus sigma u, it fails at a further value into the compressive zone. So when you use the surface, you will be conservative. Now, of course, conservative doesn't mean it's good, because you want to have a good model, a model that is able to predict safety factors accurately, not too conservatively. So we are going to use presently this model in a case where failure occurs with stresses that have to do with the first quadrant. In other words, in a case where we have a tension-dominated scenario. Because if we lie in a case where it's compression dominated, let's say in that quadrant, we would be over conservative. I don't know how conservative I am. Essentially, strictly speaking, I wouldn't be making a correct prediction, and therefore we want to avoid a misleading prediction. So when I apply the criterion in this form, in this simple form, then I want to first also check that indeed I am in the tension dominated scenario. If not, I may want to use a better model. Are there better models? Certainly, but we're not going to cover them. So having said that, let me do a quick example. So the example comes from by building up on a earlier example that we had discussed. So I'm just going to rephrase it in a new way. And I'm going to say that we have a sample of gray cast iron. Cast iron, of course, this information has to be provided to you, but just as general information, is typically quite brittle. That's what it is. Gray cast iron that's what you build your engine blocks out of. And if you've ever heard, an engine block just splits apart, fractures instead of yielding in a ductile manner. So if loaded in some incorrect manner or used improperly, so it's a brittle material. So I'm going to be concerned with its ultimate strength. And its ultimate strength is given to be 214 MPa. Now, just as a side information, in compression, the strength of this material is 770 MPa. So that's a example as to how different the strength can be in tension and compression. So we want to make sure that eventually we are in a tension-dominated scenario to use our criterion. And the state of stress is going to be such that sigma x is equal to all in MPa, 100 MPa, sigma y is equal to minus 60, sigma z is equal to 40, and then tau xy is 80, whereas tau xz and tau zy are individually 0. So I see that there is only one shear stress present, so I have a state of generalized plane stress because sigma z is not 0 with respect to the xy plane. I can find the principal stresses either with respect to the by using the eigenvalue problem, or in this case using Mohr circle, which would be easier, but we have already done so in an earlier example. So let's just remember that the principal stresses that we found earlier were, again in MPa, 133.1, 93.1, and 40 MPa. Okay. Now, I just made a note of that, but of course we need to always proceed in a methodological manner and think about what we're doing. What are we trying to do? I am trying to predict failure of a brittle material. And in general, we predict failure by taking the principal stresses and from that calculating an effective normal stress and comparing it against a critical value. In this case, I'm looking at a brittle material, and therefore the critical value is the ultimate strength. I indicate the effective normal stress with n. The function is coming from the maximum normal stress criterion. That's all I know presently. So I need to look at maximum of sigma 1, sigma 2, sigma 3. And I need to check, remember that I have a tension-dominated scenario. That's what this indicates, to make sure that I do not make a over-conservative or wrong in general prediction. Okay, so what we would like to remember or calculate presently is the safety factor against failure. So now the state of stress is a generalized state of stress. It has many stress components. So our idea is to formulate the failure or predict failure or safety factor in this case in terms of the principal stresses, and that's why we have formulated or calculated the principal stresses. So presently on sigma bar, you can easily see that the maximum value is 133.1 MPa. And that value I know is actually compressive. So I'm taking the largest absolute value. This could have been negative 133.1, and then the effective normal stress would again be plus 133.1. But because sigma 1 is negative, it wouldn't have been tension dominated, it would have been compression dominated. But it is tension dominated, so my concern is checked. There is no problem. It's a tension dominated scenario. I can compare it against sigma u. Notice that it lies in a region less than sigma u, so I'm safe. And the safety factor, therefore, is simply the ratio of the two, which is equal to 214 over 133.1 MPa, which is equal to approximately 1.61. Okay. So always the point is, if you remember the stencil and if you notice keywords in the problem that you're formulating, you're working on, then you can easily formulate the failure criterion, choose the critical stress appropriately, and go ahead and find the result that you're seeking in your analysis.